I just messaged you. What? It's like 1 over 1 so it's 1 cent. So what is the bonus? Because it says we have I know it's I just there wasn't on the company. Oh, she lied.
I see you want.
Okay.
That's shit, also,
And then
I think they're just gonna count the.
Yeah, I'm curious.
I don't even wish you could probably show where they're my menus.
Yeah.
Well, that's, whenever I got it, I literally, I actually don't even drink sodas being sort of the past few days, like, I think the past few days, I've been really good on these, in the butchers, all that, it's the only, like, just go down. And at least it's. Coloring. The name is literally on the side, like, on the coat, which is. It takes me that guy. Trade up with Sprite.
She don't think so.
I'm gonna put that poison if you have me. Keep on. Especially I started, I noticed I never like.
Okay, so let's get started. And the question we have here is actually is they're going to have a final review and put exam. I guess that's what we're going to do next week, right? So I will upload the hangout for the final review soon. Okay, hopefully by the end of tomorrow. Okay. And if you have some questions that in your midterm 1 and 2, that you don't know how to solve it, please send it to me. Then I can actually discuss those questions as well in the review sections. Okay, so what we are going to do, will the post exams open up again? I actually don't know. I mean, I can try to figure it out and tell you the answer afterwards. Okay, I don't know whether they are going to open it again or not. Okay. All right, so if let's actually a normal question. Okay, there's one more. What is the heaviest chapter on the exam, or is it equal questions for all chapters for the final exam? So next week you will be able to do the practice final exam, right? So whatever shows up there will be actually a good representation of your final exam. Okay, so use that to judge, okay, which chapter is actually more important. Okay, but you can say, you can actually think about this. CHEM1312, the design of the CHEM1312. Okay, let's start from very beginning, okay? The first thing you learn about in the beginning of this semester is what? You're learning about the definition of concentration, right? So you actually learn what is actual molarity, what is actual molality, what is mass percent, those kind of things, just definition, okay? Then we move on to the kinetics, right? So we learn about this activation energy, redetermined step, okay? And then how do we go from there to find out what would be the reaction mechanism? Then we move to the equilibrium constant, K, right? So the midterm 1 is actually preparation for your midterm 2. Because all your midterm 2 is actually start to use this ICE table to do the calculation using equilibrium constant, right? And then you start to actually use the molarity for all your calculations. Okay, so with that being said, what it really tells you is actually midterm 1 doesn't really have too many tricky questions, right? It's all about definitions. If you know it, you know it, okay? Midterm 2 is actually the one that we have actually more complicated calculations, okay? And then the one we calculate the most is what? The pH of solutions, right? So that will be actually the most important part of midterm 2, right? And that's actually part the student do the worst, right? So we want to actually make sure next week we can actually get ourselves really familiar with that calculation. Okay, so that will be actually the most important part.
In Canvas, I think there's a distribution of how much each questions, like 3 questions from 10, 11, 12, 13, and 14, including 16, 17. It says 2 questions from chapter 15, and then 5 questions from chapter 18. That will compose the entire 31 questions.
Mhm.
If anyone's wondering what the distribution was.
Yeah, it's actually very useful information, right? You can go back to the Canvas and check those things out, okay? But in the end, you can see some of the things is actually easier to understand, some of them is actually difficult to get it right, right? The one that's difficult to get it right is really the pH calculation, right? And then for the midterm 3, the one that's actually more complicated is actually to, I would say it's actually the balance of your redox reaction, maybe it's actually the one that's a little bit trickier, right? And then knowing the definition of your E cells. Okay, I will list the relevant equations when we start to talk about all those things today. Okay, and then for the chapter 18, the only calculation you do is actually only one single equation, right? Natural log AT over A0 equals next KT. That's actually only equation that you need to know, right? And then the other important part of chapter 18 is actually to predict the, oh, sorry, that's actually another one, it's actually a mass defect, right? But that one's actually more like the unit conversion type of questions. Doesn't involve too much conceptual transitions, okay? One important question for chapter 18 will be actually predict what kind of decay you're going to do, right? And that's actually where we're going to use the table that I create to make all those predictions, okay? And then chapter 16 is actually let's talk about the delta G equals delta H minus T delta S, right? And then how that is actually related to your K and related to your Q. Yeah, that's the main thing for chapter 16. Okay, so that's actually a super fast rundown about the content we're going to go through today. All right. What content in GenChem 2 transfer to organic chemistry? I feel it's a question for your organic chemistry professors, not for me, right? So because I did not teach OChem, so there's actually no way I can comment on those things. Okay, of course, your OChem professor will say, okay, I did not teach Jenkins, so I don't know how you can translate this too. Okay, so that's what's going to happen. Okay, so do I answer every questions? When do we sign up for the final exam? Next week or this week? This week? When should we sign up the final exam?
Final exam, we can sign up next week, starting 20.
Okay, 24th. Okay, see, we have knowledgeable classmates, which is very useful. Okay, so I hope we actually answer all the questions. Should we actually get started? All right, so first thing first, okay, we're going to go through a few questions for chapter 16. Okay, so but before we get started, I want to just summarize the key equations that we are going to use for chapter 16, okay? The first most important questions. Okay, let me pull the things up. Okay, the first one, of course, is your delta G is equals to delta H minus T delta S, right? So that's actually the first most important equation for chapter 16, right? And then the concept you should know is that for a spontaneous process, your delta G will be positive or negative? Negative, right? So that's actually the most important concept that you should know, okay? So this thing will actually evolve, right? So that means actually your delta G, the sign of your delta G will determine by two terms, okay? And then depending on the sign of your delta S, then your delta G will be positive or negative depending on the amplitude of your temperature, right? So those are the things that we went through last time. Okay, so that's actually the first equation that you want to know. The second important concept you want to know is actually how the delta G or delta G naught is actually connected to your equilibrium constant K, right? So the second equation you need to actually memorize that delta G naught is equals to negative, okay, don't forget this sign, okay, negative RT natural log K, okay, where K is actually your equilibrium constant. Okay, so that's actually the second most important equation you should actually know or memorize for chapter 16, right? And the third equation is you want to connect to your Q, right? So there will be delta G is going to equals to delta G naught plus, okay, make sure you know it's plus, not minus, RT natural log Q. Okay, so these are the three most important equations that you need to memorize. Okay, so of course you can actually go back to our old recorded videos and go through those concepts step by step. Okay, here I just summarized the most important equations that you will commonly used for chapter 16. Okay. All right, so and we're going to use these things to solve the problems for chapter 16 today. Okay. Any question for this? Okay. If not, let's look at our question then. Okay, let's look at this question, okay? Find the temperatures above which a reaction with delta H is 123 kilojoules per mole, delta S is 90 joules per K per mole, becomes spontaneous. Okay, so this is actually a very standard question. Okay, so the keyword here is what? Okay, spontaneous. Okay, well, every time you see spontaneous, the things that you should connect to will be delta G, right? Okay, so what other keywords you will see here? Delta H and delta S, right? Okay, so let's actually only one equation connect all the things together, which is the first equation we just talked about, right? All right, so let's actually how you get started. Okay, then you're trying to plug in all the things that you know. Okay, the only thing you want to be careful is that delta H is typically given in kilojoule, delta S is typically given in joule per mole per K. Okay, so you want to actually convert that into in joule first. Okay, so 123 convert to joule will be that much, right? Minus T that you don't know, your S is 90 joules per mole per K, right? Okay, so it says, okay, you want to know when living is going to become spontaneous and what specific temperature, right? So before you become spontaneous, the first thing to actually achieve is actually you need to reach a equilibrium state, right? So afterwards, if you go beyond that, you'll become spontaneous, okay? So what it means is actually you need to actually make this whole thing become 0 first. Okay, so I can find out, okay, this is actually my equilibrium, right? And then below, make it more negative, then will become spontaneous. Okay, so this is actually the equations that you should actually write out and solve for your T. Okay, so your T will simply equals to divided by 90, right? So if you do the calculation, then you will be able to get the answer of 1367. Okay, this will be, what's the unit? K or degree C? Kelvin, okay? So all the temperature in your calculation, you always have the unit of Kelvin. Okay, so that is actually how you solve this problem, okay? So if you know the equation, you know the word spontaneous, then you can connect your delta G, delta H, and delta S all together using the first equation. Okay, so use that and calculate your T should be actually very straightforward. All right. Question number 3. Which of the following reactions will have positive value of delta S? Okay, so it gives you 3 reactions, right? Okay. And then which one is going to give you a positive value of delta S? This is actually a very standard question, okay? And in the way we estimate this is actually very similar to the first question that we see in the previous lecture, right? Just counting the total number of gas molecules, okay? And then see if your product has more than your reactant, then it will be positive, right? So if you look at the first equation, how many gas molecule you have for the product side? 0, right? Because the product is actually pure in solid form, right? And then in your reactant side, you have 1 mole of gas. Therefore, you know your delta S is positive or negative? Negative, okay? How about the second one? Gas, gas. So for your product side, you have 4 mole of gas, right? Reactant side, you have 5, right? Therefore, your delta S will be negative. Okay. Third one, okay, you don't have gas, right? What you have is actually solid and aqueous solution, right? So aqueous solution and the solid, which one has a larger entropy? Aqueous, right? So liquid is actually have a larger entropy than the solid. Okay, gas, of course, is actually the biggest one, right? Gas is actually has way bigger entropy than the liquid and larger than the solid, right? Therefore, you have 3 more of liquids on the product side. You only have the solid on your reactant side. Therefore, you know your delta S will be positive. Okay, so it's a very simple conceptual type of questions. Okay, but the key is actually to know the gas has the largest entropy than the liquid, than the solid. Okay, so of course the aqueous solution considered as a type of form of liquid. All right, so that's actually how you solve question number 3. Number 4. Okay, calculate the value of delta G naught in kilojoule for the combustion of 1 mole of butane with the molecular oxygen to form carbon dioxide and gaseous water using the value of delta G naught formation below. Okay, So there are two things that you want to know for this question. First, actually, it provide a very detailed description about what the reaction you're going to have, right? So the first thing to do is actually you could translate that description into a balanced equation. Okay. So butene is C4H10. Okay. And I say it's going to interact with oxygen, which you should know is actually O2, right? And then it's going to form carbon dioxide, which is CO2 plus water, right? So you need to actually write this out first, okay? And after that, you need to actually balance that specific equation, okay? So starting from the non-hydrogen, non-oxygen atom first, okay? You have 4 carbons here, right? So you know, you need to actually multiply 4 for your CO2, okay? And then once you have this, okay, here you have 10 hydrogen, right? So therefore, you need to actually multiply 5 for your H2O. Okay, so once you do that, then you start to counting how many oxygen you have on the product side. So you have 8 plus 5, that's 13, right? So you need to actually multiply 13 over 2 for your oxygen. So you need to balance the oxygen out. Okay, so let's actually count the first step. You need to actually make sure you have a balanced reaction equation. Okay. So if you have no problem with this, then we can actually proceed to calculate the delta G of the overall reaction, right? And then delta G of the reaction can be calculated the sum of the delta G knot formation of your product minus the sum of delta G knot formation of your reactant. Okay, so this calculation is actually the same if you want to calculate the delta H of the reaction or delta S of the reaction, right? So the only thing you want to be careful is that when you do this, you want to actually make sure you actually multiply the coefficient accordingly, okay? So in this case, the product that you have is CO2 and H2O, right? So the first term, then you're going to have 4 times the delta G knot formation of your CO2, okay, which you can find here, right? So it's negative 399, okay, plus the delta G knot formation of your water, which is negative 225, okay? And the reason I multiply 4 is because the coefficient of your CO2 is 4. I multiply 5 here is because the coefficient of your H2O is 5. Okay, so that's actually the things that you have for your product side. Then you need to actually minus the things that you have for your reactant side, right? So for the C4H10, the delta G knot formation is 1 times negative 16. Okay. And then you should do 13 over 2 times the delta G knot formation of your O2, right? You have delta G knot formation of O2 here. You don't, right? So what does that mean? Yes, this is 0. This is 0. Okay, so the delta G knot formation, okay, for many substances, they actually equals to 0. Okay, for example, the molecules exist in its natural state. Okay, the delta G knot formation will equals to 0. Okay, for example, O2. Okay, oxygen, the natural state is actually O2 in the gas form, right? So scientists actually define the delta G knot formation for your O2 is equal to 0. Okay, how about the delta G knot formation of your H2 gas? It's also 0. Okay, how about nitrogen gas? N2 is also 0. Okay, So if the substance is actually presented in its natural existing state, the delta G naught formation is typically 0. Okay, if it is 0, it won't show up on the table. Okay, so if you do this calculation, you realize, okay, how come I did not get the delta G naught formation of some substance? I feel like I need to use it. Okay, most likely it's because its delta G naught formation is simply equals to 0. Okay, so this is actually how you calculate it. Okay, so once you do all these calculations, then you are going to get a value of 2705. Okay, this is going to have the unit of joule. Okay, sorry, negative. Okay, negative 2705 joule. Okay, so this is actually how you calculate it. Okay, recap. Okay, important thing is actually you first need to have a balanced equation. Okay, because those coefficient matters. Okay, so once you know the coefficients, then just apply this simple calculation. You should be able to get the delta G for the reaction. Okay. So let's see how you solve question number 4. Okay, number 5. The equilibrium constant of a reaction is 0.35 at 25 degrees C. What is the value of delta G naught at this temperature? Okay, so what's the keyword here? Equilibrium constant and delta G naught, right? So it's very straightforward. Okay, so the one that connected these two directly is actually delta G naught is equal to negative RT natural log K. Okay. So the R is 8.314. Temperature is 25 degrees C, right? So it's 298 K. Your natural log K is 0.35. Okay, so once you do that calculation, you will get a value of 2601 joule. Okay, but you want to have the kilojoules per mole. Okay, so you actually divide 1,000, so it will become 2.6 kilojoules per mole. Okay, so this one is actually relatively simple. The one that will be a little bit more interesting will be if let's start to tell you, okay, for less specific reactions, I give you the concentration of your reactant species. Okay, then once you see less specific information for the reactant or product, okay, it actually implies you can actually use the equation that contains Q, right? Therefore, we can use our third equation, delta G equals to delta G naught plus RT natural log Q to do the calculation. Okay, we actually went through a question like that when we do our chapter review for chapter 16. Okay, so if you're not familiar with what I'm talking about, go back and rewatch that. Okay, they will actually cover most of the calculation you're going to encounter for chapter 16. All right, so let's pretty much all the things that you need to know for chapter 16. Okay, any questions?
I have a question. It was something on the, I think it was a practice test about changing the voltage of the cell. I understand that we use that equation where it's like the constant over
We
and.
haven't gotten to 17 yet.
Oh, this is 17. I thought this was 16.
No, it's 17. Okay. So this is actually pretty much the things that you will need to know for chapter 16. Okay, now we're going to start review the chapter 17. Okay, so let's talk about the essential equation for chapter 17. Okay, for chapter 17, the things that matter the most is, again, you want to know how your delta G naught is actually connected to the E naught cell. Okay, the cell potential. Okay, so the delta G naught is equals to negative N times F times your E naught cell. Okay, N is the number of electron got transferred between your redox reaction. Okay, F is the Faraday constant. E naught cell is actually the cell potential. Okay, and those things will actually connect to your delta G naught. Okay, so one thing that you should know is that for the E cell and the delta G, okay, there's actually a negative sign to connect them together. Okay, so previous would say if you have a spontaneous process, your delta G will be negative, right? So the same thing will apply to this the E cell, okay, because there's a negative sign in the front. Okay, so if you have a E cell is positive, then it will become a spontaneous cell, okay, meaning it will be a galvanic cell or the voltaic cell. Okay, so those are the concepts that you should know. Okay, and then again, the important thing here, okay, we are going to use the E cell or E naught cell for the chapter 17, right? You still want to actually connect these things to your K, to your Q, okay? So the equation I ask everybody to memorize is that your E naught cell can be connected to your K using this equation, 0.025693 divided by the number of electrons that transfer between your redox reaction, K times natural log K. Okay, so make sure you memorize this one is actually positive. Okay, there's actually no negative sign like your delta G. Okay, and then to connect to the Q, okay, you want to remember E cell is going to equals to your E naught cell minus 0.025693 divided by the number of electron got transferred times your natural log Q. Okay, so these are the equations that will be very useful when you do the calculation in chapter 17. And then compared to 16, you can see the logic is actually very similar, right? In chapter 16, you use delta G as the main thing that connect your K and connect to your Q. But in chapter 17, you use your E cell to connect to your K and the Q. Okay, so these are the sets of equations that's going to be very important for your midterm 3. Yes, any questions? No questions? Yeah, questions? Okay. All right, so another very important question for chapter 17 is actually the electroplating, right? So the equation to actually memorize that. The mass of your product that's going to form on the electrode can be calculated using the M, which of your current times the time in seconds, divided by the number of electrons got transferred, divided by your Faraday constant, multiply the formula weight of your product, right? So this is like another equation that you can memorize. So you can just solve those electroplating type of questions.
Yeah.
Okay.
Is that N value that we use specific to the species that we're looking for the weight of, or do we use the balanced one? Where like, let's say one species was like a 3 electron transfer, the other one was a 2 electron transfer. Do we use the common factor of 6 for that? For N?
So for the electroplating, typically you don't have late concern. Okay. Only thing that matters is actually when you're actually going to be reduced. Because typically when you do an electron plating, it's actually the reduction reaction of the chaos, right? So you just need to care how many electrons you needed for reduce one chaos species. We're going to go to play this question for this. All right. Okay, so these are the 4 most important equations for chapter 17. Okay, the other big thing for chapter 17 is actually to balance the redox reaction. Okay, so we are going to go through 2 more examples so you can just get familiar with the process. All right. Okay, so consider a vortex cell based on the half reaction below. Okay, Ag plus electron give you Ag. The reduction potential is positive 0.8 volt. The cobalt 2 plus 2 electrons that give you cobalt solid. The reduction potential is actually negative 0.28 volt. Identify the cathode and give the cell voltage under standard conditions. Okay, so in order to form a electrochemical cell, okay, you must have a pair of oxidation and reduction reaction, right? And then in most of the questions you're going to see, or pretty much all the questions you see, when they give you that E naught, okay, it's all for the reduction reactions, right? But for the cell, you need to actually have 1 oxidation, 1 reduction. Okay, that means actually to flip one of them. Okay, so you have the oxidation process occur simultaneously. Okay, and here the keyword is what? You have a vortex cell, right? So sometimes you see vortex cell, sometimes you'll see galvanic cell. Okay, so every time you see those keywords, what it's trying to tell you is that your E cell has to be positive, right? So with that being said, that means actually if you flip one of the reactions, okay, your inner cell will actually become negative, right? Because now it becomes the inner oxidation, they become your oxidation potential. Okay. And you add up your reduction potential and oxidation potential of the 2 half reactions. It has to be positive. Okay. So with that being said, you should be able to see the one you need to actually flip will be the second equations, right? Okay. So that you add up the 2, you'll get positive value. Okay. So you need to flip this one, right? So it will become cobalt and become cobalt 2 plus 2 electrons. Then your E naught oxidation potential should equals to positive 0.28 volt, right? So first, you actually know you have galvanic cell, then you need to actually decide which half reaction to actually flip, so you can get the oxidation potential. Okay, and then you can add up your oxidation potential and the reduction potential. After adding up, it has to be larger than 0. Okay, so the only possible choice you have here will be actually flipping the second half reaction. Okay, so once you have that, then you can actually add up you can calculate your E cell, which is going to equals to your reduction potential of your Ag, and then the oxidation potential of your cobalt, right? Okay, which is going to equals to positive 0.80 plus positive 0.28. And they will give you 1.08 volt. Okay, so let's actually your E cell. Okay. So which one is actually your cathode? You want to decide what is your cathode, what is your anode, right? So the easy way is actually, like I say, I always teach you guys to write out what is actually low rock, what is actually your G rock, right? Okay, so your low rock will be your anode, right? Your G rock will be your cathode. Okay, so G rock is actually gain electron, right? So which one is actually the one that gain electrons? Is your Ag plus gain electrons, right? So you will actually form the Ag, okay, and that will be actually your cathode. Okay, therefore your cathode will be your Ag. Okay, So this is actually how you go through this type of questions. Okay, any questions? All right, so if not, that's what it is. Okay. Question number 7. What is the balance equation for the galvanic cell reduction that represent the notation below? Okay, so this is actually a notation that you have. Okay. So you should know that the notation actually start from, there are a few things that you need to know. Okay, let's start from the simple one. Okay, what does this represent? Bridge, right? Okay. Okay, so for the midterm 3, I would strongly encourage that you know exactly the structure of the galvanic cell. Okay, and know what is actually anode, what is your cathode, where is actually your soul bridge. Okay, and how the electron was actually flowing in the cell. Okay, we went through a lot of things in our lectures. Okay, so you want to actually get familiar with that structure too. Okay, so this thing is actually your soul bridge. Okay, the things on the left hand side of your soul bridge will be your are you saying it's actually correct? Okay, so the things on the left will be your two half reaction, right? One is actually LoRa, one is actually G-Rock, right? So it starts from LoRa to G-Rock, right? So on the LoRa side, you have SN2 plus becoming, so this is AQ, becoming SM4 plus. This is AQ. Okay, but you also have this PTS, right? And then for your G-Rock, you are going to have Br2 liquid, Br minus AQ, and then PTS, right? So you can see a lot of species actually presented there. Okay, but some of that is actually not relevant to your redox reaction. Okay, every time you see PT, okay, this guy, okay, it just serves as an electrode. It doesn't actually involve in your reaction. Okay, but if you don't know that, you get very confused. You don't know what are the real reaction you are going to look at. Okay, so this PT is simply the electrode. It doesn't actually involve in the reaction. Okay. And the reason you need to add an electrode is because the reactants and the products you are going to look at, okay, they doesn't exist in the solid form. Okay, for example, here the things that matters is actually these two, right? One is actually SN2 plus, one is actually SN4 plus. They are ions, they are not solid, so they cannot serve as an electrode. Therefore, in the PT. Okay, the same thing for your G-Rock. Okay, you have Br2 and Br minus. They are not solid. They can actually use as an electrode by itself. Therefore, you add in the extra electrodes, PT. Okay, so and then this, I choose different color. Okay, so this and this will be actually your LoRa and G-Rock. Okay, so the way you write all those notation, you always start from the reactant and then the product. Okay, so with that being said, you should be able to write out that your LoRa is actually SN2 plus and then becoming SM4 plus. Okay, and then your G-Rock should be Br2 liquid becoming Br minus AQ. Okay, so that is actually the things that you should be able to actually write out. Okay, so once you write these things out, then you start to look at this. Okay, you want to actually balance the atom first. Okay, so for the LoRa, the atom has been balanced. Okay, so you don't do anything. But for your GROC, you know, you need to multiply by 2 for your BR minus. So you have the BR balance. Okay. And then after that, you will need to actually balance your charge, right? So for your LoRa, on the left-hand side, you have +2. Right side, you have +4. Therefore, you know you need to add in 2 electrons so that the charge will be balanced. Okay. For your GROC, this is actually 0. This is actually -2. So you add in 2 electrons, right? So after that, then charge is balanced. And then this number, they will agree with each other. Then all you need to do at the very end, just add up all those things, right? So the electron will cancel out. And then in the end, what you're going to get is SN2 plus BR2 liquid. Okay, this is actually AQ. That's going to become SN4 plus 2 BR minus. It's all in the aqueous form. Okay. So this is how you get to the final balanced reaction from a cell notation. Okay, so again, you should really know what the notation means, right? Those two lines represent the soul bridge, right? And the things on the left is actually your LoRa, the things on the right is actually GROC. Okay, if you see PT, you know that it's actually electrode. Sometimes you actually use the other type of electrode is just carbon. Okay, so the commonly used electrode is PT or carbon, okay, or C, okay. So sometimes you're going to see people use just carbon to serve as the electrode. Okay, so PT carbon is the commonly seen electrode. Okay, so once you know they are electrode, they are actually irrelevant, right? And then you look at that reactions, you should know the things on the left. It always starts from the reactant and product for your LoRa. So you can actually write out that 2 half reactions without any problem. Then you balance the atom, balance the charge. Okay, make sure the electron got transferred and accept between the 2 half reaction, they are the same. And you adding all up, you get your balanced redox reaction from a cell notation. Okay, so those are the processes you need to actually go through to get the correct answer. Okay, any questions for this? Okay, so if not, let's go to the next. The question says the standard cell potential for a dry cell battery is 1.6 volt. What is the standard free energy for this cell? Okay, so what are the keywords here? Cell potential, right? Standard cell potential is one keyword. The other keyword will be the standard free energy, okay? So translated things into, this will be your E naught cell, right? Standard cell potential is actually your E naught cell, okay? Standard free energy change will be your delta G naught. Okay, and then we know this two is connected using this equation, right? Delta G naught is equal to negative NF E naught cell. Right, so that's actually the first equation that we write out when we start to talk about the key equation for chapter 17, right? So you know that is actually the equation you're going to use. All right, apparently you have to calculate your delta G naught. Then it's actually to know the information of your N and then your E naught cell, right? So your E naught cell is what? 1.56, right? So you know this is actually 1.56. F is just Faraday constant, right? Which is 96485. Okay. The only thing that's actually unknown here will be your N, right? So you want to figure out what is actual electron are transferred between your reactions, right? Then you want to actually start to analyze your equation, okay? So I'm going to move these things a little bit. Okay, zinc oxidation number will be good. Manganese oxidation number will be +4, right? Because O is actually -2. You have 2 O, that's -4. But overall, the species is actually neutral. Therefore, your manganese will be +4. Okay. NH4, your N is +1, right? Okay, so this one should be lowercase, my bad. Okay, NH4 plus. Okay, so your N will be -3. Okay, so here N is also -3. Manganese here will be +3, right? Because you have 3 oxygen less -6. Okay, and the overall molecule is actually neutral, right? And you have 2 manganese. Therefore, each manganese is actually +3. Zinc 2 plus, this is actually +2, right? Okay, so H2O, H is actually +1, O is -2. Okay, so if you look at this, what is actually the species that undergo the redox reaction? The oxidation number changes for your Zn and then Nm, right? So your Zn change from 0 to +2, right? And then your manganese go from +4 to +3. Right? Your nitrogen actually still stays the same. It's all -3, right? So this is actually another species that undergo a reduction or redox reaction. Okay. So who is actually your LORA? Zinc, right? Because the oxidation number increase. Okay. So if zinc solid becoming zinc 2 plus. Okay. Your G-rock will be MnO2 becoming Mn2O3. Okay. So those are the 2 half reactions. Okay. Okay, now it should be 2, right? Okay. So now you want to actually see how many electrons got transferred between the 2 reactions, right? So on the top, how many electrons will be actually donated? 2, right? Okay. So for the bottom, how many electrons is going to be accepted? So the manganese here is actually +4, right? This is actually +3. Okay. So for each manganese, you need 1 electrons, right? I have 2 of them, therefore you will need 2 electrons. Okay. So for your LORA, you give out 2 electrons. For your GRA, you need actually 2 electrons to balance out that charges. Okay. Therefore, you know your N will equals to 2. Okay. So once you know your N is equals to 2, what you need to do is actually go back and plug in 2 into the specific equation. Okay. So once you plug those things in, you're going to get a value of 300,950 joule. Okay. But I want you to actually represent the answer in kilojoules, right? Yeah. Yes, negative, sorry. Okay. So but you want to convert into kilojoules, so you divide it by 1,000. Therefore, you got 301 kilojoule, okay, with a negative sign in front of it. Okay. So this is actually how you use the keyword to connect to the specific equation to do the calculation. Okay. If you know what equation to use, if you know how to actually count the number of electrons got donated and accepted in your two redox reactions, then you should be fine. Okay. Any questions for this? Now then, let's do some interesting questions then. Balance the following reaction in basic solution using the lowest possible integer. Okay, given the coefficient of water. Okay, so this is actually very standard redox balancing type questions. Okay, so again, you want to actually first identify the oxidation number of your species, right, of your atoms. Okay, so oxygen carries -2, right? You have 4 of them, therefore it's -8. The overall molecule carries -1 charges, therefore your manganese will carry positive +7, right? Okay. You need to practice this a lot when you go back home, okay? Because this is actually always a step that I feel students actually did not actually get those numbers quickly enough. Okay, it's going to slow you down too much. Okay. Br minus, okay, -1. MMO2, okay, each oxygen is -2, right? So this is actually -4. Overall is neutral, therefore your manganese is actually +4. BrO3, 3 oxygen, that's -6. But overall is actually -1. Therefore your Br will be +5. Okay. So once you write these things out, then you start to see, okay, whose oxidation number has increased. This one, right? Going from -1 to +5. Okay, so this will be your LoRa, right? Therefore, the other one will be your G-Rock. Okay, then you can write out this. Your LoRa will be Br minus, becoming BrO3 minus. Your G-Rock will be MnO4 minus, becoming MnO2. Okay. So once you identify the two half reactions, the next thing is actually you want to balance the atom, right? So you want to balance the atom that doesn't belong to your oxygen, doesn't belong to your hydrogen, right? So here you want to actually balance your Br first. Okay, so 1 Br on the left, 1 Br on the right. You're done with Br, right? Then you can actually go to work on your oxygen. Okay, so this is in a basic solutions, right? So if you're missing oxygen, you use 2OH minus, right? If you're missing one oxygen, you actually add in 2OH minus on the other side, right? And then if you're missing protons or H, then you use H2O. Okay. So that's actually in the basic solution, right? What happens if you are under an acidic solution? Then H, you want to use H plus, right? O, you want to use H2O. Okay. And always start from your O, then go to your H. Okay. All right, so get back to here. In the basic solution, therefore, we know we need to actually compensate that using your OH minus first, right? So you have 3 extra oxygen on the product side. Therefore, you need to add in 6 OH minus on the left-hand side, right? Okay. So once you do that, you are going to introduce some extra protons on the reactant side. Then you want to actually compensate for that using the water, right? So what you're going to do is actually you're going to add in 3H2O on the product side. Then you actually balance out all the oxygen and hydrogen. Okay, so if you look at this, you have 6 oxygen, 6 hydrogen on the left-hand side, right? On the right-hand side, you have 3 oxygen and then 3 oxygen, total also 6 oxygen, right? And then here, you have also 6H. Okay, so by doing that, you actually balance the atom for your LoRa. Okay, let's look at second one, your G-Rock. Okay, start from your right? It's already balanced. One is actually MMO4, the other one is actually MMO2, right? So the is actually done. Now you look at the oxygen. On the left-hand side, you have 4. On the right-hand side, you only have 2, right? So on the left-hand side, you have 2 extra oxygen. Therefore, you want to balance the oxygen. Therefore, you add in 4 OH minus on the product side. Okay, and once you do that, you want to actually balance out your proton. Therefore, you add in 2H2O to balance out the protons. Okay, so by doing that, you're going to balance all your hydrogen and the oxygen. All right. Okay, so after that, then you need to start to balance your charge. Okay, so if you look at here, you have -6, -1, that's -7 on the left-hand side. Okay, on the right-hand side, you only have -1, right? Therefore, you need to add in 6 electrons to balance out the charge. Okay. Similarly, for your G-Rock, right? Here on the left-hand side, you have -1. On the right-hand side, you have -4. Therefore, you want to add in 3 electrons to balance out the charge. So that both sides will be -4. Okay, so after that, then you will start to look at this. For your LoRa, you give out 6 electrons. For your G-Rock, you only uptake 3 electrons, right? They are not balanced yet. Okay, you want to actually make sure they are balanced. And the way you do is actually you're going to multiply 2 for your G-Rock. Okay, so that the G-Rock will actually uptake 6 electrons. And after that, then you can actually add up the 2 half reactions, right? So once you do that, then you will get 6 OH minus plus Br minus plus 6 electrons plus 4 H2O plus 2 NNO4 minus. Okay, so those are the things that you're going to have for your reactant side. For your product side, you're going to have BrO3 minus plus 3 H2O plus 6 electron plus 2 MnO2 plus 8 OH minus. Okay, so you get a very long equation. Okay, then you start to actually cancel out the things that you are on both sides. Okay, so 6 electrons, 6 electron will cancels out, right? 3 H2O, there are 4 here, therefore this will only have 1 H2O remains. 6 OH minus, therefore only 2 OH minus remains. Okay, so if you conclude this, then you are going to have Er minus plus H2O plus 2 MnO4 minus, that give you BrO3 minus plus 2 MnO2 plus 2 OH minus. Okay? And then the question is asking what? The coefficient of water, right? Then the coefficient of your water will simply equals to 1. Okay, so this is actually how you solve this type of question. Okay, so you have to get really familiar with the process. Okay, so we actually went through a few very interesting questions in our recording lectures. Okay, so I would strongly suggest that you go back and recheck all those examples to get yourself really familiar with all these processes. All right. Any questions for this? Okay, so let me see. I want to do one more practice together with you for this type of questions. Okay, so this is actually the questions that I want to go through together with you. When the reaction Cl2 becomes Cl minus plus Cl3 minus is balanced in the aqueous basic solution, what is the coefficient of water? Okay, so it's the same process. Okay, Cl2 AQ becoming Cl minus plus ClO3 minus. Okay, so again, you need to actually assign the oxidation number first, right? The oxidation number of your Cl2 will be 0, right? So this is actually 0. Cl minus, apparently this will be -1. Okay. ClO3 minus, you have 3 oxygen, right? So that's actually -6. But you have -1 overall, therefore your Cl in this case will be +5. Okay. And then if you analyze this, you'll realize that, okay, you only have 1 reactant, right? So that means actually this guy will actually undergo LORA for this, but you will undergo G-Rock. Okay. So all you need to do now is actually, okay, I write down my LORA will be Cl2 becoming ClO3 minus. My G-Rock will be Cl2 becoming Cl minus. Okay, so sometimes you actually get confused. Okay, I only have 1 reactant. How do I actually write out my LORA and G-Rock? Okay, the fact is actually, okay, if you only have 1 reactant, it's actually you can do both. Okay, so this is actually how you handle it. Okay, so once you do that, then you start to actually balance your atom, right? So 2 Cl on the left, only 1 here, therefore you actually multiply 2 to balance out your Cl first. Okay, and then you look at your oxygen. You have 6 on the right-hand side, right? So therefore, you want to add in this is in the basic solution, right? Okay, so this is basic solution. Therefore, H, you use H2O. Missing O, you use 2OH minus. Okay? You're missing 6 here, therefore you add in 12OH minus. Okay? Once you add in 12 OH minus. On the other side, you want to add in 6 H2O to balance out the H. Okay, then you finish the balancing of your atom for LoRa. For your G-Rock, it's a lot simpler, right? Just multiply 2 for your CO minus, then it's done. Okay. All right, so then up to this point, we're done with the balancing of the atom. Now we start to balance the charge, right? For your LoRa, you have -12 here. Here you have -2. Therefore, you know you need to add in 10 electron here. Okay. All right, so then for the bottom one, you have -2 here, right? Therefore, you know you need to add in 2 electron here. Okay, then you finish balancing your electrons. Then you look into your LoRa, it gives out 10 electrons, but for your G-Rock, you only uptake 2 electrons. Therefore, you know you need to multiply 5 for your G-Rock, so that the electron that transfer between two half direction will be the same. Okay, so once you do that, you can actually add up all the species here. Okay, so you're going to get 12 OH minus plus Cl2 plus 10 electrons plus 5 Cl2. That's what you're going to get for your reactant side. For the product side, you're going to get 2 ClO3 minus plus 6 H2O plus 10 electron plus 10 Cl minus. Okay, so once you write these things out, then you start to cancel out the things that show up on both sides, right? 10 electrons will cancel out. Okay, so then you can actually condense all these things. You got 12 OH minus plus 6 Cl2. That give you 2 ClO3 minus plus 6 H2O plus 10 Cl minus. Okay. And then what? Yeah, go ahead. How do I know I need to add in 10 here? Okay, it's because on the left hand side, I have -12, right? You have 12, -1, so that's -12 on the left hand side. On the right hand side here, I have -2. Okay, so it's not balanced. Therefore, I add in another 10 electron. So on both sides, you have -12. Cool. All right. So get back to this point. Okay, so I want you to be very careful. Okay, this could be actually the step that many students will miss. If you look at this final equation, are they actually at the lowest integer? It is not. Okay, therefore, you need to further simplify this equation by dividing all the coefficients by 2. Okay, so the final equation you should have is actually 6 OH minus plus 3 Cl2. That give you 1 ClO3 minus plus 3 H2O plus 5 Cl minus. This should be your final balanced equation. Okay. And then the question is asking the coefficient of water, right? Therefore, the answer should be 3. Okay. And then I want to draw your attention to the question again. Do you see? Okay. Yeah, so be very careful. Okay. So they will always have a question like this. You want to make sure that the equation, the final equation that you get is at its lowest integer form. Okay, if you can actually make it simpler, then make it simpler. Okay, and then provide the answer based on that simplest form. Okay, but this is actually the question I want to actually go through and let you know. Okay, sometimes it could be actually very tricky to give the correct answer. All right. Okay, so yes, we still have time for the final questions here. Okay, so this is actually a question for you. Okay. So it says, how many grams of chromium metal can be played out when a constant current of Am is passed through an aqueous solution containing Cr3- ions for 40 minutes? Okay, so the equation we are going to use, okay, the keyword is actually played out, right? So it's actually a very standard electroplating question. Okay, and then the equation we're going to use is the grain of your product is going to equals to the current that you supply for certain amount of time in second. Okay, divided by the number of electrons that you will need to produce one more of your product times your Faraday divided by your Faraday constant, and then multiply the formula weight of your product. Okay, so that is actually the equation you're going to use. Okay, here we know the current you have is Am, right? So the A is equal to A. Okay. The time is 40 minutes, but you need to actually convert it into second. Therefore, you need to actually multiply 60. Okay. Number of electrons. Okay, so this actual part you want to be very clear about what is actually N you should actually provide, right? So inside your solution, what you have is actually Cr3-, right? And then the product is chromium metal, right? The metal has the oxidation number of 0, right? So basically go from 3+ to 0. That means actually to gain 3 electrons. Okay, and that's actually the N you can actually provide here. Okay, so 3 is actually the things that you can actually write down here. Okay. And then you need to actually multiply the Faraday constant, okay? 9, 6, 9, 6, 4, 4, 8, 5, right? And then multiply the formula weight of your chromium, right? So this actually time to check out your periodic table, find out the formula weight of your chromium metal. Okay, and then we check it out, the molar mass will be 51.996. Okay, and then when you compute that, you should be able to get a value of 3.45 grams. Okay, and that's actually how you calculate this type of questions. All right, so any questions? It's actually Cr3+ becoming Cr, and then you need to actually supply 3 electrons to make that happen. Okay, and then that's actually how you determine your N. Okay, so those are the things that you should know for chapter 17. Okay, I think there's actually one more questions I put somewhere that I want to actually go through together with you. Oh, okay, this one. Okay, this is actually another type of question. Okay. The value of the E naught cell for this specific reaction is 1.7 volt. Calculate the delta G naught for the reaction at 25 degrees C. Okay. This actually, again, previous actually went through that cell notations, right? So that you know, your LoRa will be Cr becoming Cr3+. Your G-Rock will be Hg2 2+ becoming Hg. Okay, so and then you want you to ask, okay, calculate your delta G naught. Okay. And then it tells you your E naught cell is equals to 1.78 volt. Okay. The equation that we tell you to actually connecting these two is actually delta G naught is equals to negative N times F times your E naught cell. Okay. In this questions, it tells you E naught cell already, right? What it want to ask you is actually, can you actually know the proper N for this reaction? Because if you know the N, then just plug into this equation, you can calculate your delta G naught. Okay. Now the problem is actually, how do you actually go from your cell notation to figure out your N? That's actually things that many students will actually miss. That's why I want to have this example show up here. Okay, so we sort of went through, okay, how you can read this one and write out your LoRa and GROC already, right? Now you want to actually start to balance all the things. Okay, so first, balance the atom. The first one is already balanced. The second one, you need to add in 2 to balance out the atom, right? And then you need to balance your charge. You need to add in 3 electrons for your LoRa. Okay, for your GROC, you actually gain 2 electrons. Okay, so after writing these two, then you realize that the electron that got generated from your LoRa doesn't equal to electron got accepted by your GROC, right? Therefore, this has to multiply by 2. This one need to multiply by 3. Okay, therefore the net equation should be 2 Cr plus 6 electrons plus 3 Hg2, 2 plus. That's going to give you 2 Cr3 plus 6 electrons plus 6 Hg. Okay, and then 6 electron cancels out. Okay. But the important thing here is actually you should know the total number of electrons got transferred between these redox reaction. The N should equals to 6. Okay. This is actually a part that most students will miss. If you just look at that cell notation, sometimes it's actually misleading. Okay, so you want to actually write out this LoRa and GROC. Make sure the electron got transferred between the two half reaction is the same. Okay, therefore you can actually determine your N is equal to 6. Okay, so by doing that is you can calculate your delta G naught is going to equal to -6 times your Faraday constant. I always cannot remember the number. 96485. And then times 1.78. Okay, and then if you compute that, you should be able to get the number of -1030463 joules. Okay, and then convert it to kilojoules, then you got -1031 kilojoules. Okay, that's actually how you get to that answer. Okay, but the key is that you need to know how to compute the proper number of electron gun transfer between the two half bridges. Okay, this is especially confusing when the question only give you the cell notation. Okay, so be careful of that. Okay, so this one should conclude all the things I want to go through today. And thanks and good luck with your midterm 3.
I have a question.
Mm-hmm.
So